Okay, here we are in chapter 1 on ingredients of change, functions and limits. Now we're in section 1.2, which is function behavior and in behavior limits. So we'll start with the behavior of real-world functions is usually described verbally by words such as a growth, a loss, an increase, or a decrease. And so graphically, how does that look? Well, graphically, the behavior is read from left to right as the input value increases. So, you look at a graph from the very leftmost part and you read as you go right. Now, if the output increases along the way from left to right, the function is defined as increasing. And as you see here, as we move from left to right on the x-axis, on the y-axis, it's going up, and so therefore it's increasing. And so that would be an increasing. Now we can also look at it in tabular form for increasing, for example. The same would work with decreasing and constant. But you start with year and you can see that the years are going up from, so basically we're going from like here 2000 all the way over here to somewhere in 2008. And then we look at the output. This is the output here. And so we start at 5.6, then 5.8, 6.2, 6.7, 7.3, and we see that every time it's going up. And so from 2000 all the way up to 2008, we're going up. Now, what the actual curve shape looks like, I don't know, but it's a slow, gradual going up. So that is also an increasing thing, but it's in tabular form instead of graphical form. Now, if the output decreases along the way, the function is then defined as decreasing. And as we can see, as we move from left to right, we're going down. The output is going down. So basically our y values are getting smaller. For a while, it kind of gets slower, but then it goes back down again and starts going down. Now, if there's no change in the output as the input changes, the function is defined as constant. And that basically means we have a straight line straight across, there's no change, and that would be a constant function there. Now, on those functions, we have something called concavity. And this is basically the curvature of a function graphically. Now, we have either concave up or concave down. Now, if we go back to here, if we think about this, we're going concave up because this point is pointing upwards. So that would be up. Now, concave down, that would be kind of this point. We're concave down here. Now we're concave up at this point. So there is a point here in between that it's changing from concave up to concave down. But that's what they kind of look like. It's going up and facing up, or in this case, it's facing down. Okay, so and again, concave up if a graph of the function appears to be a portion of an arc opening upwards or facing upwards, that's concave up, and concave down, it's that arc is opening downwards or facing downwards. And then we also saw that inflection point on a continuous curve, it's the point where the concavity of the function changes. And we can see that here, it's probably right here about 1. So it looks like it's about there, and that's still up, and then at that point, then it starts going down. And so we have at the point 1 on the x-axis, the concavity changes, and so that's the inflection point. So now what we want to do is, for example, identify the direction and concavity of the function shown in each figure. For graphs showing a change in behavior, an inflection point, indicate the input intervals over which each type of behavior occurs, increasing, decreasing, concave up, concave down. All right, so let's just start here with this one. And so we'll say, what is it? Well, if we look, it's kind of a decreasing one, but it's kind of facing up. So we'll say it's concave up, and it's decreasing. And we really don't have a change of behavior. It's continuously decreasing and it's continuously concave up. All right. So what about the next one? Well, the next one, we have this point here and it looks like, well, that looks concave down there. But then if you start noticing this point here, that looks concave up. So we're going to be concave down, and this is going to be increasing. So we'll put the two together. So it's increasing. And that's from basically everything up to here. We're increasing to about B. So we're increasing basically everything less than B. So basically, how do we want to write that? Less than B is going to be where it's going to be. So everything less than that, it's increasing. And then we're going to have concave up, concave up, and it's going to be decreasing. All right, so concave down is going to be all the way up to the point, looks like right there. And that's going to be our point of inflection. So let's call a point of inflection the C, okay? So that means now we're going to be decreasing basically from B on up. So we're going to be decreasing everything greater than B. And it's going to be concave up. Well, it's concave down for everything less than C. So it's going to be less than C. It's going to be concave down. So we kind of really should have had 1, 2, 3, 4, 5, but that's okay. And we have concave up from point C forward, so greater than C, and it's decreasing again like that point there. Okay, so we had a lot of different pieces here that we actually kind of should have talked about, but again, each piece is showing where it's at. Now this one, it's always decreasing the whole way, and it's always concave up, so we don't have to represent anything there. Now this one is a little bit more messy because we're going up and down and up and down and up and down. So we're going to have a lot of concave up, concave down. So let's say we have concave up, we'll have a concave down. And so where is, and we'll just kind of write where they're first where they're at. So concave down. Well, if we think about this, this is concave down because it really is something that looks like that. So it's going to be from this point here, since we start there, it's going to be from -4, and then it's going to be basically less than x, and it's going to be less than. Now, where does it switch? Well, it switches, it looks about right here to being concave up. And so that's probably about a 3 here, so that's halfway, so that'd be about -3.5. Okay, so it's concave down from -4 to -3.5. Then it's going to be concave up from -3.5 to, well, now it's going to go all the way down. It's going to come all the way up here. And about right there is probably going to switch. So that's going to be probably -2.5, it looks like. And then we're going to switch over to concave down again. So it's going to be from -2.5 to, and it goes to about -1.5, I think. And then from -1.5 less than x, so we're going to go from about here to about there, which is a -0.5. And then here from -0.5 less than x less than, now we're going to go to a +0.5. Now that means we're going to start here at a +0.5, and we're going to be concave up all the way over to here, which is 1.5. And then we're going to be at 1.5 less than x, and then we're going to go from here to here, which is going to be 2.5. So then we'll be 2.5 less than x, and so we're going to be up going from about 2.5 to about 3.5. And then from about 3.5 less than, and then the chart stops here, the graph stops here, so it's going to be less than 4. Okay, and so those are the concave up and concave down. Now our decreasing and increasing, how does that work? Let's get rid of that extra drawn in piece so now we can look at just the graph itself. Well, it's decreasing from here to here. All right, so maybe we'll start another decreasing and increasing. So it's decreasing from -4 less than x less than, and then that's right at the -3. Now we're increasing from here. We're going up, 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 up to right at that peak. So it's going to go from a -3 less than x to -2. And then from here, we're going back down again. So we're going to go from -2 less than x less than, we go to -1. Now from -1, we go up here to 0. So -1, oops, less than x less than 0. We don't need a comma there. And so now from here to here, so from 0 to 1, we're decreasing. And then from 1 to 2, we're increasing. And then 2 from 3, we're decreasing again. And finally, from 3 to 4, we're increasing one last time. Okay. And so our points of inflection are basically going to be where it switches from one to the other. And it looks like, this is going to be a point, this is going to be a point, this is going to be a point, this will be a point, this will be a point, this will be a point, this one, and this one. So kind of when we hit here, we're going with the concave down, then we're flipping over and we're going concave up. Now we're flipping over, going concave down again. And so each one of those points are points of inflection. So if we want to write points of inflection, those are going to be at, what is that, negative 3.5, and then negative 2.5, and then negative 1.5, and then there's going to be a negative zero point 0.5, and then we'll have a 0.5, and then a 1.5, and a 2.5, and a 3.5. So those are kind of where they are. And those kind of line up where we're changing from concave up to concave down, basically. So that kind of is what we'd expect. Okay. So that one's a little more detailed and it has a lot more points we have to actually come up with than the simple one, especially the first one here. Okay, so that's how we're going to look at the inflection points, increasing, decreasing behavior, concave up, concave down. All right. What about this one? So we have the flu. In the fall of 1918, a worldwide influenza epidemic began. It's estimated there were 20 million deaths. And I've actually seen that this is 50, but our book says 20. But I've seen most of the places I've read it's 50 million. So I would probably disagree with the book there, but maybe all the places I've read about are wrong and this is right. Who knows? And 50 million deaths worldwide from the flu before the epidemic ended in 1920. A model for the number of deaths among members of the U.S. Army in the first 3 months of the 1918 influenza epidemic is graphed below. So we have this graph here. And so we want to do A, use the graph to describe the behavior of A, which is the number of deaths here, curve, as increasing, decreasing, or constant. Well, if we look, it's increasing and increasing and increasing and increasing and increasing. And this looks like it could keep going up and up and up. So we're going to assume A is increasing. Okay, and we're going to say it's just increasing continuously and it doesn't change. Now at this point, maybe it flattens out, but I'm thinking that that's just their model up until 12 weeks. What about this went on for 2 years? So I'm thinking that really it's just a gradual. It's just going to keep increasing as we go. Now we want to know the concavity of A. If there's a change in concavity, then we want to know the approximate input value where the concavity changes and tell how it changes at that point. Okay, so we look here, this looks like it's concave up, okay? Now it looks like somewhere in here, we're switching because now we're concave down. So this is up, this is down. And so we have concave up, and basically from 0 less than x, that's a less than, and now we have to kind of decide where is it at. So it's somewhere in between here. I'm not exactly sure, but it's 6.1, something like that. It's hard to say with this kind of graph and actually doing that. So maybe we'll just say it's less than 6. Okay, so it's concave up from that point there, and that means the inflection point is at x equals 6, approximately, we'll say, because we're not exactly sure. It's somewhere in that vicinity. And then it's going to be concave down from basically 6 greater than 6. So we can say x greater than 6, at least with what it shows here. okay? And so that would be x greater than 6. And if we wanted to, we could say less than, but then we don't know where that stops there. So we'll just say everything greater than 6, it's concave down. Okay, so that I think gives us everything we need. If there's a change, that's the inflection point, and how the concavity changes at that point. Well, it changes from going concave up to going to concave down. So basically, you know, we're zooming up here, and now we're kind of slowing down, and so therefore it kind of starts that concave down. Okay. All right, so the end behavior of a function refers to the behavior of the output values of a function as the input values become larger and larger. So basically, as they increase without bounds, so they go to positive infinity, or they become smaller and smaller, basically decreasing without bound, going to negative infinity. So we're looking at the end behavior, and so we're looking at everything on the right side and everything at the very left side. So we're looking at both sides. What does the behavior do at those ends? So we have three possible end behaviors. One, the output values may approach us an equal or a certain number. So maybe they approach 0. So maybe as we come down, then the behavior approaches 0, never reaches it, but it approaches it. Okay. The output values may either continue to increase or decrease without bound, go to either positive or negative infinity. Well, in this case, we're going to 0, but this way, if we're saying we're going left, if we're going to negative infinity, well, that means it's going to go without bound to positive infinity. And so that would be kind of something where it would go without bound that way. Or the output values may oscillate and never approach a particular value. And if you remember, that's kind of what we had over here. It's oscillating up and down, up and down, up and down, okay? And this would be one, as x gets smaller and smaller, it looks like it decreases without bound. This one, it appears it's approaching 0. This one, it looks like it could be increasing without bound and then decreasing without bound, unless it really flattens out more and we can actually come up with a thing. So those are kind of the ways the end behaviors work. All right, so I'm going to stop there and do another part of the lecture in a little bit.